I want to give a talk today, giving a kind of perspective, because it's frontiers and new perspective in geometry and physics. So I would like to give a perspective from far away of certain areas in the theory of integrable systems, in which real normalized differential play a central role. So the modular spaces, this is a kind of plan of the talk. The modular space of curves with a pair of real imaginary normalized differentials are central for many aspects of the algebraic geometrical integration theory. So what is real normalized differentials? One can say just it's meromorphic differentials on a curve whose periods are purely real, all periods. This kind of normalization is very simple, natural, and doesn't depend on any choice of basis of cycles. It is unconventional for algebraic geometry, where people prefer to deal with holomorphic objects, and for that you need to fix a basis of cycles, which makes your theory on the modular space of curves with fixed basis of cycles, which is a point of Teichmüller space. My goal is to see or to apply the objects that came from the theory of integrable systems to the study of geometry of modular space of curves with punctures. And that's the only way to normalize or choose differentials which is independent on the choice of cycles. And this object is central, as I said, in many aspects of the theory of integrable systems, but recently they became instrumental for a certain class of problems in pure algebraic geometry. Although this real normalization is frightening for algebraic geometers, it turns out that they provide a tool which is very useful in the study of problems in pure geometry. I'll present some recent results in this direction. But first, let me explain how this kind of object come to life in various aspects of the theory of integrable systems. So let me start with the Witham theory, where they arose. So the Witham theory is a theory which can be seen as averaging theory for nonlinear partial differential equations, which is generalization of classical Boголюбов-Krylov method of averaging. So it's applicable to any system of nonlinear equation having a certain set of exact solution having the form. So there is a periodic function, and depending on a certain number of parameters, and the dependence on the x, y, t, and other variables is through its linear motion on a corresponding torus. So u, v, and w are vectors. So you have a quasi-periodic function of variable x, y, and t. So having such class of solutions, one may want to extend and construct a wider class of solutions, and actually one needs to do this in order to solve some basic problems in the theory of KdV, nonlinear Schrödinger. Whenever you have problems with certain boundary condition, it's pretty common that you cannot use only quasi-periodic solution. You need to extend this class. So you start to look at asymptotic solution of the problem whose leading term is given by the exact solution of your system. So you have exact solution, and now you want to perturb it and construct a full formal series of perturbation, which and if you assume, which is clear, that this phase is defined through a function of slow variables x, y, and t, and you define this S through this equation, then definitely the leading term is a solution of original equation up to the first order. Then all other terms of the equation you define from non-linear, non-homogeneous linear equations, where the linear operator is just linearization of your non-linear equation on the background of known solution. So we have a recurrent system of non-homogeneous linear equation, and they are solvable because it turns out that this linear operator, which is a linear operator with non-constant coefficient, is integrable. A full basis of solutions of this equation is known, as well as the dual basis of the adjoint equation. So you can easily write the solution in the form of series. Unfortunately, the corresponding formal series become unreliable on scales of variables of order epsilon minus 1. Epsilon, I recall, this is a small parameter of your perturbation. So the equation which describes the drift of integrals of your original equations, so adiabatic dependence of your integrals, are in general called Witham equations, although there is no systematic scheme to obtain them for abstract equation. So the Witham equation for KdV equation was postulated. I will stress they were not derived. They were postulated from some arguments, not rigorous one, by Flaška, Forrest, and McLaughlin. And the idea was the following. The KdV equation is integrable, so there is infinite series of integrals of motion. You write them in a local form. Then you just replace Pn and Gn, which are differential polynomials in terms of original equation, and put the average, and you postulate that this equation, integrals of motion, should hold on average. Unfortunately, this approach is not applicable to 2 plus 1 integrable equation because there is no local integrals of motion. And the corresponding system of equation was derived in my early work, and they were derived at the condition that the first term of the formal series, of this formal series, this first term is bounded. So if you require that this is bounded, sorry, then you get a system of equations that looks very simple, although the derivation is highly non-trivial, and the system looks as a zero curvature generalization, as quasi-classical limit of zero curvature equations written in terms of certain real normalized abelian integrals. This is so in zero curvature, usually omega j, there should be I here, are Lux operators. Here you just replace them by kind of symbols which are abelian differentials. They're kind of symbols for the corresponding differential operators. It turns out that this equation can be brought to a Flaška, Forrest, McLaughlin form. So you just define certain function E from this set of equation, and then if you use this E as a local coordinate, you come to the conclusion that all equations of Witham equation are linearized, so they exist a prepotential or generating function, and if you write the generating function in such a form, you introduce a function Q which satisfies quasi-classical analog of string equation. Then you define the tau function in a very simple way, and this is how two differentials, E and Q, come to life in the theory of integrable, in the Witham theory, as well as the tau function of the Witham equations. Okay, so there is a way to solve rhythm equation, and the way solving rhythm equation is similar to the solution of Riemann-Hoff equation via Godot transform. So on the modular space of curves with a pair of differentials, you introduce a certain certain set of functions which provide a system of local coordinates. Then you just invert this map and you get a solution.
Local coordinates where?
On the modular space of curves with on the total space. So the way of solving, you just introduce a function and you invert, like in Godot transform. So what are these coordinates on the modular space of curves with pair of abelian differentials? In this way, I'm not really use any real normalization because the theory admits extension to the modular space of curves with a pair of abelian differentials without prescribing any constraint on their periods. So the set of local coordinates is the following. This is periods of one differential over cycles, periods of another differentials over all cycles. This is 4G complex coordinates. Of course, it's local coordinates. You can prescribe these coordinates only after choice of basis of cycles. Globally, they are not well defined. The other part of differentials is globally defined, and it's of coordinates is a globally defined. It's roughly speaking, you can think about them as fixing singular part of multivalued abelian integral, which is ds. I recall that ds is q dE. So we have q e gamma, and you define certain differentials q dE. So if q and e are meromorphic, this expression has its own singular part. So you fix singular part or coefficient of the expansion of this ds in terms of a local coordinate provided by one of the local coordinates. And the remaining set is a period of this ds over ak. So you can prove that it's almost everywhere a certain system of local coordinates. To be more precise, and we'll come to this point later because it's a very important locus where these functions are not local coordinates. So on the open set, which is a complement to the set of curves with a pair of differentials where these two, where the zeros of these two differentials do not intersect. So generically, you have a curve, two differentials, their zero sets, their zeros are some independent sets. Whenever they do not cross each other, the coordinates I described before are really coordinates. And the study of this locus, singular locus for rhythm coordinates is actually, as we'll see, very hard and important problem. So there are, as I said, there are two sets of coordinates which are the most interesting for me. So besides the rest, so there are periods over cycles of one differentials and there are periods of another differentials. As I said, this is ill-defined functions. They are functions only if you choose a basis of cycles. But the condition that these periods remain constant is independent on the choice of a basis. So fixing periods of differential defines a foliation structure on the modular space. So locally, or you can think about it as a projection, a well-defined level set of this function on the modular Teichmüller space. You project them, and on the modular space of curves, it becomes a foliation structure. So leaves of big foliation is the locus along which the periods of one of the differential are constant. This is the definition. And so we coming close to the main subject of my talk. So this is the modular space of gamma, E, Q. You really don't need the second difference. So it's a leaves of foliation. Leaves along which the periods of dE are constant. Again, you cannot prescribe the given constant, but it's well-defined foliation structure. It turns out that if you restrict your tau function on the leaves of this foliation, then the derivatives of within tau function satisfies this remarkable formula, which was known for AN models in works of Waffa, in works of D. Graf, Verlinde. And so the claim that Witham tau function restricted to a leaf of big foliation provides a solution of VDVV equation. I have to, so in case of G equals 0, it was my original result. Then it was generalized by Dubrovin for the case of Hurwitz curves. I would like to point out that this condition, these leaves of foliation, there are some special leaves, or there is a special leaf along all these periods are zeros. So if periods of differential are zeros, then this is a function. So you have a modular space of curves with a function having prescribed degrees of orders of poles at certain points, which is a Hurwitz curve, Hurwitz space. So you can think about leaves of a big foliation as a generalization of the space of Hurwitz, Hurwitz curves. I have to say that if periods are zeros, then the corresponding Witham tau function is homogeneous. So when I say that they provide solution to the associativity equation, it means that they are indeed solution to associativity condition, except the condition, which sometimes is crucial, that this function should be quasi-homogeneous with respect to times. So leaves of the big foliation, and how these objects come in the theory of topological quantum field models. But having two differential allows you to make a connection with another subject, namely, suppose we fix all coordinates except the last one, except the coordinates which were just the periods of ds over a cycles. Suppose we fix periods of QE together with singularities. Then you remain with the locus, which is in general smooth, of dimension G. G is the genus of the corresponding curve. And the Jacobian bundle over this G-dimensional family is an integrable system. And it turns out that all known integrable systems fell into this framework. So they're always described as a level set of all integrals of all Witham coordinates corresponding to the modular space of curves with a pair of differentials. When I started, Leon?
You started at 7.
Okay, I have plenty of time. And the corresponding symplectic form is just given by this formula. So this is the connection of the modular space of curves with a pair of differentials to the Hamiltonian theory of integrable, finite dimensional integrable systems. But it turns out...
Sorry, what is the total dimension of your moduli space?
The total dimension, of course, depends. So what we have M, okay, well, that's what I'm talking. We have mg and m, which is the multiplicity of differentials at certain number of points. M multiplicity of others. So overall, it is 5g minus 3 plus sum of n alpha plus m alpha plus 1 minus 1. So you carefully count the number, the dimension. So fixing periods, subtract 4g here. Fixing singular part, subtract this. So you're left with g variables, which you choose as periods. So whenever this set of coordinates is gain of coordinates, and I describe where they are coordinates, you have a smooth g-dimensional locus. Over this g-dimensional locus, you have a Jacobian bundle, which give you 2 g-dimensional phase space. And the claim is that choosing various n and m multiplicities, you can get phase spaces of all integrable systems considered. So it's a general framework that unify theory of integrable, finite dimensional integrable system. They come as a natural finite dimensional systems like Kallanger-Moser, Toda, or describing some finite dimensional systems which are invariant submanifolds in the space of solutions of partial differential equations. And it turns out that precisely this framework is the same what is needed for the Witten-Seiberg ansatz. So according to Witten-Seiberg, the quantum modular space of n equals 2 supersymmetric gauge model should be described by a family of curves with a differential, which is a meromorphic one form such that its derivatives are holomorphic differentials, and then the prepotential is determined by the periods of this differential d lambda. So you have one set of variables, another set of variables, a, k, and bk are adjoint, canonically connected basis of cycles, then the prepotential of Seiberg-Witten model defined from this set of equations. And it turns out that the family of curves and differential together come as a solution. So you choose a modular space of curves with applied differentials. You make this locus, and this d lambda can be identified with the generating differentials in the Witten theory.
Lambda there is what?
ds. So ds is exactly d lambda. So ds was introduced in the theory of Witten equations, and actually, you see, Witten and Seiberg, they described that you should have a modulus, a certain ansatz. They didn't provide a solution. It was solved. The solution for this ansatz was obtained in our joint work with Fonck. So we proved that this common level set of this function gives you a family.
But in that language, here for ds, you don't need a dual. You don't have that.
No, I don't need. But no, I don't need. I have a Witten tau function. All what I need to prove that this Witten tau function satisfies this equation. I am not defining prepotential from this equation. I'm just showing that Witten tau function, which was introduced in a way I described before, is a solution. So it comes with a family together with already a solution of the prepotential. So the prepotential is given by the formula I gave before for Witten tau function. So its connection with integrable system of this ansatz was in our joint work with Gorsky, Marshakov, Mironov, and Morozov. And in full generality, the identification of d lambda with ds is in our work with Fonck. But actually, this d lambda or ds, as you wish, in the theory of integrable system was introduced much earlier in works of Novikov and Veselov in the definition of analytical Poisson bracket. They just described exactly the ansatz you need to have analytic Poisson brackets. Also, as Witten and Zeiberg, they didn't get a solution for this ansatz, which this solution was obtained in our work with Fonck. And recently, but I'm going to talk in the remaining 40 minutes, it turns out that besides of integrable systems, this construction provides a tool for certain problems in the geometry of modular space of curves with fixed points. So the modular space of curves, smooth, I stress, it's smooth curves, have curious vanishing properties. So,
And K is the number of punctures?
yes. So, you see, this is a smooth orbifold, manifold of dimension 3g minus 3 plus k. But it turns out that unlike the compactification by Deligne-Mumford compactification, which gives you a projective variety, the most interesting question about how far this open part of the modular space from the affine space. And the first result was obtained by Diaz, who proved, okay, if you have a affine space, there are no complete cycles inside at all. So you can see how far your modular space from projective, where the whole space is the biggest cycle, just looking on what are dimensions, maximum dimension of complete cycle in MG. So there was a remarkable theorem by Diaz, who proved that actually in MG, I recall that this is the space of dimension 3g minus 3, there is no complete cycles of dimension bigger than g minus 2. The next result was proved by Layenga, who proved that ring of tautological classes vanishes in dimension bigger than g minus 2 plus k. Tautological class is a class generated by Mumford-Morita classes and lambda classes or k classes, which are defined here. This is the basis for this ring. And LG is a canonical bundle over modular space of curves with punctures. Okay. And later they were generalized and combined in the famous Faber conjecture, who conjectured that the tautological ring of MGK looks like the cohomology ring of a compact complex variety of dimension g minus 2 plus k, again, which is much less than 3g minus 3.
And explain the g minus 2 before.
Yes. And so it's a dream of everyone just to find such a cycle. Probably it's a wrong idea. There might be no such a cycle. Because I have to say the following, that it's only upper bound. So if you look, are there any cycles, complete cycles in the modular space of curves? You will be surprised that all known constructions of such cycles provide cycles of dimension of order log g. And there is no even a clue how to get a bigger cycles. I can explain why. So how you define a family of curves in the modular space of curves? If you write any equation, of course it would be singular. It will be the generations. One example, one construction is due to Kodaira, who suggested consider a curve of genus G0 and consider 3 sheeted cover branched only at one point. For two-sheeted cover, there is no branching at one point. And that's why if you consider the family of such covers, there would be degenerate curves, because these 2 points, for example, for double cover, will collide and provide singularity. For three-sheeted cover, you have a smooth family of curves parameterized by point of ramification. The genus of this cover is 3G naught. You can iterate now. And you have a family of curves of genus G, roughly speaking, of dimension log 3G. So it's completely open question, are any family with linear dependence on G? Moreover, recently Witten asked me, is there any construction of curves with punctures? So you have curves with k punctures, not distinct punctures. In this modular space, namely in MGK, is there any analog of Kadeira construction? Can you construct a family of curves? Because points collide, it's much harder to produce a smooth family. The answer, I don't know. The upper bound you will get relatively in the way I'm going to explain very easily, but it's going to be, again, of the order of G. So it's open and very interesting and important for physics application question. What are complete cycles? Are there any construction of complete cycles in the modular space of curves with k points? So, widely accepted by algebraic geometers, experts, explanation of the existence of these vanishing properties is the existence of certain affine stratification or existence of certain cover of the modular space by open affine sets. No conjecture how these sets should like. The only the explanation comes if such exist, then okay. The importance of this kind of stratification was first realized by Arbarella, who considered the stratification of the modular space of curves, smooth curves of genus G, by loci of curves on which there exists a point, Weierstrass point of order n. So if this curve can be realized as n-sheeted cover with total ramification in one point. So W2 is a locus of hyperelliptic curves. This is a locus of trigonal curves ramified at one point, and so on. So there is this stratification of the modular space, and it was conjectured that this complement is affine. It turns out it's a hard result, but it turns out it is not. I'll come to some Arbarella conjecture a little bit later. So recently, using this Witten approach, we jointly with Gruszewski proposed a new geometric explanation for these vanishing properties based on the fact that the modular space of curves with punctures and some additional data are spaces affiliated like it was in the Witten theory. So now I'll consider the modular space of curves with punctures and a jet of local coordinates. So this is the modular space we are interested in. If we consider the order n equals 0, then it will be the modular space of curves with punctures. So this modular space is a space of real analytic foliation. Again, this is the total space foliated by leaves. And the existence of these leaves is, together with the next ingredient of the construction, is what explains all these vanishing properties, curious vanishing properties in algebraic geometry. And moreover, so there is a foliation, but it's a real analytic foliation whose leaves are complex. So they are complex. Real analytic structure only in transversal direction. And on this modular space there is a set of continuous functions which restricted on leaves of foliation are piecewise harmonic. And the first one is subharmonic function. So subharmonic function is a function that satisfies maximal principle. So what are these functions? But first of all, let me just explain once again what is real normalized differentials and what is essential. So the identification of this modular space of curves with punctures and local coordinates is through identification of these local jets of local coordinates with singular parts of real normalized differentials. And for any fixed set of singular parts, there exists only one differential whose normalization is real. Okay. So leaf of the foliation, which I described before, is always a complex, smooth, complex subvariety of real codimension to G. So what are coordinates along this leaf? The coordinates along these leaves are described as follows. So you have a differential. The number of zeros of this differential is exactly the dimension of a leaf. So you take, so they are critical points for function, multivalued function, which is just a abelian integral. And if you take critical values of this abelian integral, these are like generalization of parameterization of Hurwitz curves by critical points, critical position of branching points. And this is the generalization, a generalization of well-known result for Hurwitz curves. So if you...
Question.
Sure.
In terms of that example of Seiberg-Witten, this equation of the reality is some equation on the local coordinates A's, when A cycles itself, right? Can I think about the equation that the imaginary part is 0 as certain restriction?
Yes, you can. Yes.
And what is the meaning of that?
Let me go.
Does it have a meaning in Seiberg-Witten?
In Seiberg-Witten,
that's an equation on the coordinate itself.
at this moment, I don't know the meaning of this condition
But it's not holomorphic equation.
It's not a holomorphic condition. Okay. Okay, so as I said, these critical values of abelian integrals are, of course, ill-defined function because it's a abelian integral. But imaginary part of this value is well-defined and independent on the path. So it's a locally well-defined function on the modular space. So if we choose all of them, we get a set of functions, continuous function on the modular space, which are restricted on a leaf, becomes a set of piecewise harmonic function, and F naught, biggest one, is subharmonic function. Now I just want to revisit from this point of view Diaz theorem and prove it just in one line. So suppose X is a complete cycle in the modular space of curves, and consider its pre-image on the modular space of curves with 2 points. A curve with 2 points define a real normalized differential. So if we have a curve with 2 points, we can define a unique differential of the third kind having 2 poles with residues I and minus I at these 2 points, and all periods real. There exists only one such a differential. So critical values of these differentials is a set, you can be seen as a set of functions, f naught f to g minus 1, defined here. So if we consider the preimage of our cycle, it's going to be a complete compact cycle in mg in cg2. So this is the square of a universal curve. So on this z, the function f naught is a compact cycle, it's a continuous function. So this function has a maximum. Now, if we take a point where f naught achieves its maximum, then it achieves its maximum on the intersection of z with a leaf. But on a leaf, this is subharmonic function. So it cannot have a maximum unless it is just this intersection is zero-dimensional. So it must be a constant. If f naught is a constant, then all other functions are constant. So intersection of z with L is at most zero-dimensional. So z intersects L transversally generically. So the dimension of z, codimension of z, we know. So that's it. This is the end of the proof of Diaz theorem. Because leaf has codimension g, so the z cannot be of dimension bigger than g. This is the whole proof. Actually, there was for 40 years it was known Arborella conjecture, who conjectured that if you consider a complete cycle of dimension g minus n, it must intersect the locus of curves that have a Weierstrass point of weight of order at most n. If you look in the book of Harris and Morrison, Modular Space of Curves, you will find that 4 sections I describe how hard and impossible to prove this conjecture. This conjecture was known for 40 years, more than 40 years. It turns out that again, using the similar structure with a modular space of curves with a meromorphic differential of the second kind, you can prove actually this Arborella conjecture. Okay, I have no time to explain how overcome this difficulty, but okay. It's another application and open problems in this area. So, as I mentioned before, Witham times are coordinates on the locus where 2 differentials have no common zeros. So, and this locus where 2 differentials have common zeros is a locus of singularity for the Witham equations. And generic problem, central problem, to describe the maximum number of common zeros of 2 differentials. To see what is connection of this. So, and what we are trying to prove, or we made the conjecture that this number is bounded by this number. Unfortunately, okay, until now we cannot prove it, but it's I provide a very convincing argument for this conjecture. Sorry?
You become physicist.
Okay, you see, I'm giving a talk using computer, so. Okay, so what is the convincing argument? there is a classical problem. What is the maximum number of cusps for a plane curve of degree d? So you have a plane curve of degree d. This is a curve in C2 defined by this equation. And you're asking, what is the maximum number of cusps? Because what's the connection of this problem with the previous one? If you have a cusp and you can see the normalization of this curve, the differential d log w and dw and dz have a common zero at the preimage of a cusp. So the total number of cusps and the total number of common zeros. So you can think about common zeros as the cusps of the curve. So there are certain construction of a curves with a lot of cusps, because curves with the cusps come as a branching covers of a surfaces. You have algebraic surface, you have its cover over CP2, and actually this cover is branched over this curve, and this curve typically has singularity like double nodes and cusps. So there are certain constructions of such curves, and the best known result is due to Kulikov, who constructed a number of curves. Okay, it's relatively easy exercise to show that with the degree, number of cusps grows as a square, d square. So there is a construction of curves with this number of cusps. Actually, it's a little bit surprising, because if you think about what you should expect, the dimension of the plane curves is, roughly speaking, d squared over 2. I'm writing about the leading term. This is the total dimension. Having a cusp is a condition of codimension 2. So you expect that you have expecting dimension of this of a model space of curves having certain number of cusps is 2 over k. So if it's positive, so you expect that the number of cusps should be of order d squared over 4, 0.25. So it's much higher than expected number of cusps. On the other hand, there are very powerful tools needed to get an upper bound. The best upper bound was, until recently, was obtained by Hirzebruch, and it was 0.31. In 2004, Lander, using generalization of Mayaka-Yau inequality, proved that this number is 0.309. So right now, this maximum number of cusps is squeezed between 0, 30, 91, and 29. So our conjecture with corresponds, which we exactly in the middle. Is it convincing or not? I don't know.
There are many rational numbers.
Yeah, I know, but it's not a proof. But you see, we came to this conjecture just from study of Witham equation, and only later on I found that this.
You think it's optimal?
I think so. I think that actually we have a 3 over 10 is it's optimal, and it coincides with the bound needed for Cassini conjecture. There is a lot of coincidence, so it's very convincing for me. Probably wrong one. And finally, the most recent development in the theory of differentials with real normalized differentials. It turns out that it's connected with another very hot topic today, the theory of Amoeber's Ronkin function, non-Jampere measures. Okay, so let me recall. You have an equation defining in, you think about f as a Laurent polynomial in many variables, although I will need only 2 of them, so my main interest is n equals 2. Amoeba, by definition, is the image of this locus, zero locus, or zero locus defined by one equation. So you have equation f1, f of z1, zn equals 0, hypersurface. And you consider it's mapped to real space defined by absolute value, log absolute value of the coordinates. The image is called amoeba. For example, and this term was introduced by Guilfand. And if you look at typical amoeba of algebraic curve defined in C2, so take n equals 2, the equation defines algebraic curve, plane algebraic curve in C2, and you look, so you have a curve defined by equation f of z1, z2 equals 0. You project it into R2 by the amoeba map, and you will find that the image would be just a bunch of tentacle-like tentacles going to infinity with a bunch of holes. So this is amoeba. This is the complement, and it's known that the number of the complement, connected component of the complement is bounded by the number, by arithmetic genus of these algebraic curve, or the number of integer point in the Newton polygon. And the identification of connected components of the complement with integer points of the Newton polygon is defined by the gradient of another object very important in the complex analysis, so-called Ronkin function. So this is a function which can be defined for any f. So you take log f, integrate all of this cycle, which is the preimage of x under this log map. So the preimage is a torus. You integrate, you get a number defined on x, and this is called the Ronkin function. Okay, I'll skip it. And there is remarkable inequality proved by Passare and Rulgard, saying that the amoeba is unbounded, it's going to infinity, but the area of this amoeba is always finite, and it is bounded by area of Newton polygon. And there is remarkable characterization of famous Harnack curves, extremal curves, in terms of this inequality. So it's Michalkin and Rulgard. They proved that if area equal to its supremum, then this amoeba map is at most 2 to 1, and the curve is actually real and is simple Harnack curve. It's a special class of curves having maximum number of fixed integrals of maximum number of fixed cycles under involution. I have seven.
No, you started 3.
Okay, then 2. Now, how we can think about amoeba? So what is essential here? I claim that actually you can define amoeba not just for a curve defined by the equation. You can define the notion of amoeba for abstract curve. You have a curve with the punctures. So what is amoeba for this curve? You just take 2 real normalized differential or imaginary normalized differentials. Then the real part of abelian integral is a single valued harmonic function. If you have 2 differentials, you have a map, which is amoeba. Remarkably, it turns out that, okay, I have 2 minutes, so I'm not going to go into the full theory of generalized amoeba. I would like to comment on to have one other look on what is real normalized differential and why they so often come to life in various objects. So, real normalized differentials. Differential. Let me just do it. Imaginable normalized. It's the same. It's the same as harmonic function. Almost the same. So if you have a curve with punctures, then for any harmonic function, you can always define, so x be a harmonic function. Then there exists always a dual harmonic function. You can form a local holomorphic function on a curve with punctures. It's not a function because this dual is defined up to a constant. But if you take the differential of this object, d zeta, it is a differential with all, by definition, all periods pure imaginary. So saying imaginary, so the theory of imaginary differential, imaginary normalized differential is the same about harmonic function. It's nothing more, except a little bit more. You just specify what is the boundary behavior at the punctures. Just saying what kind of pole this function will have. Because generically, if you take arbitrary harmonic function, the corresponding differential will have essential singularity at punctures. So, considering imagine normalized differential, it's just you specifying some behavior of the function. Okay, and now the fact that should be in all textbooks of complex analysis, but surprisingly, I ask all experts, no one knows this. Now, suppose you have two harmonic functions in some local domain. Then you can form two conjugated functions, which you can consider as functions of x1 and x2 as a local coordinates here. So having two harmonic functions, you can use them as a real system of coordinates. So you can consider dual function, harmonic function, as a function of x1 and x2. Simple exercise says that there exists a function rho whose gradient is y2 minus y1. So for any pair of harmonic functions, the dual one are generated by one function. And this is the Ronkin, or precursor of Ronkin function, which is a convex function.
What is